A lot was said about dispersal, population genetic structure, and I want to be clear on the application side what we're talking about here. In 2006, we had guys who were from BC who were saying that it's possible that these populations that arrived in places like Whitecourt and Fox Creek and Grand Prairie arose from de novo, arose from pre-existing populations that had been sitting there, lurking there for 5,000 years, and then they erupted simultaneously. They said that we couldn't rule out that possibility, which is true. So I'm happy with the work that the population genetics guys have done, showing that there's no way in heck that these guys aggregated from in the landscape around and erupted as a result of these movements into epicenters. There's no evidence for that at all, because these beetles appear to be quite a bit different from neighboring beetles. They don't match beetle populations out in Wilmore, and what they do match are mountain pine beetles located up in the Tumbler Ridge region of BC. So they've got that match, suggesting that gene flow is related to dispersal, i.e. the 2006 populations really did fly in. They really did fly 200, 300 kilometers. And so, again, echoing a point that Felix made, mountain pine beetle are active dispersers. And they're not just active in 2006 when they came over the Alberta-BC border into this region of Alberta down here, and they didn't just do it in 2009. They're not just dispersing quickly through this forested landscape, they're also dispersing very quickly through this unforested, largely unforested boreal plains landscape. So the line between where you see mass attacks and the line between where you see endemic populations is really quite large, and they're dispersing quickly through that. On occasion, they're dispersing quickly through that band. So the leading edge is actually really a broad band, about 100 kilometers wide, again supporting Alberta's, the way that they approach mountain pine beetle management, which is a zonal approach, and they do tend to focus on wide belts of areas requiring action. And I have one arrow here pointing to this wide band out here where you've got endemic populations, very hard to treat, very hard to detect, but they're there. And then you've got this other area down here where you've got dispersal coming in from the north, dispersal coming in from the south, and the question that Felix was just asked about the possibility of them mixing, a high possibility that they'll mix down in here if they ever get around to, those populations get around to growing and erupting. But there's something that's holding them back from doing that. And you heard a lot of talk about overwintering biology and genes that can confer cold tolerance. Felix made the amazing point that 13% of 1,000 markers are associated with metabolic pathways associated with cold tolerance. That's phenomenal. There's a phenomenal genetic basis for a new race of cold tolerant beetles arising in northern Alberta, and these guys are going to be right on top of that as that process goes forth. And it's a question now of what are those genes linked with? What are those alleles linked with? What other traits? If there's no cost to evolving cold tolerance, they'll do it very, very quickly. So you have to ask the question, what are the costs of evolving cold tolerance? A really good question. With practical applications, because the province does its risk ranking system on the basis of a stand susceptibility index that's weighted by different parameters relating to the pine proportion of pine, the age of pine, the DBH of pine, and then climatic suitability. This is the single most important component that we know of affecting mountain pine beetle population dynamics. And so Felix just gave a whole spiel on winter survival and how that can change over time and space as a function of evolutionary processes. Even if an area is protected by, say, a cold climate, such as this area down in the southern foothills, even if it's protected historically by cold climate, if they're evolving cold tolerance by beetles coming down through Hinton into this area, you could have a new race arising there where those barriers are completely gone and your equation now does not hold up. And then you're left wondering why the heck these beetles came in, grew up in such large numbers when the model said that that shouldn't happen. Well, the value of studying genomics is you're studying the ecology of surprise. This is a system capable of a lot of surprise, and we're poised to observe that surprise. This is a graph that I explained last week, but I want to put it in some context. This is a graph of US data that plots population growth rates versus infestation levels. So as populations, these are negative exponential curves showing very fast population growth rate, and then for very high populations, they tend to collapse, and population growth rates are very, very low. So that's why all these curves have a negative exponential shape. It's a classic shape in ecology. What you see are a family of curves that are fit to a time series of mountain pine beetle in Idaho. And so these population growth trajectories down here are what you expect, what you observe actually in cold years like 1991 and 1993. And these curves up here are what you observe in really warm years, such as 2004 and 2002. And this is from a paper in 2009 where Jim Powell and Barbara Bentz show that almost all of the dynamics of mountain pine beetle growth over time is attributable to changes in the summer climate and the attack dynamics. And you heard Nadir gave a great talk about the aggregation attack dynamics, the ability for beetles to find each other and to find susceptible hosts. If that process, according to these guys in Idaho and Utah, it explains 85% of the variation in population growth rates. So Nadir's studying, he's got his finger on the button of the process that explains almost all of the eruptive dynamics in the US Rockies, the Southern Rockies. In Alberta, we think we have a second component to this in terms of the winter biology. So what we need to study in Alberta here is how these curves fluctuate randomly. Ooh, that hurts. How these curves fluctuate randomly up and down in response to changes in weather, and how these curves migrate deterministically from the cool to the warm in a slow rate as a function of deterministic changes in climate resulting from, for example, greenhouse gas forcing. So it's a very integrative model that you have right here, but it's not been calibrated for Alberta. It has been calibrated for the US. We need to make fast progress on that. The other point is that I discussed all these negative exponential curves, this family of curves, and how this curve shifting up and down from 1993, 1991, 1995, this shifting of curves explains all the variation in these data points. The other point I want to make on this graph is the title of the graph is two contrasting models. The Powell and Bentz model is this family of negative exponential curves that are fit through these dots, this time series. But the other graph shown in here are the classical curves, and Janice showed you the parabola that you get on a well-defended tree where at certain low densities, populations are not able to grow. Below those attack densities, they actually decline to extinction. And this is a model espoused by Alan Berryman and actually parameterized to this exact, not to this exact time series, but a closely related time series in Glacier National Park. And he suggested that population dynamics are a function of host defenses at this low density, so a parabola fitted to the time series, and then endemic population growth on suppressed hosts when populations are in their endemic phase. So according to the Berryman-Raffa model, this system erupts when this curve here intersects with that curve over there. And so it's a very different model of the dynamics, and we need in Alberta to resolve that difference. To what degree are dynamics driven by this multiple equilibrium type system versus a single equilibrium type system described by negative exponentials? And we think it's probably a mix of both, but we can't answer that unless we have physiological experiments in the field that quantify how this curve flexes from way up here to way down here when defenses are altered as a result of either pine species or environmental factors such as drought. So these curves can flex dynamically and they can flex spatially in response to host genetics. We need that model badly. We needed it like 10 years ago, but this slow progress, so at least we have a framework for doing the integration. The same kind of model that I just showed back there, that was actually an analysis not of population data, but it was actually an analysis of annual rates of change in areas infested. You can see log base 10 cumulative hectares infested. And so we can also do those kinds of analyses on Alberta data, and we need to do that fast. We need to do the exact same kind of analyses, but where we're including things like that Felix mentioned, winter and summer climatic suitability. Janice mentioned the climate moisture index in years prior to population growth. Kathy mentioned the host tree genotypes, and Nadir mentioned how the host trees vary in their defensive capacities, their ability to repel beetles. All these layers can be used as inputs to a parameterizable models, if that's even a word, parameterizable. Mountain pine beetle sex ratios. I don't have the map that Felix showed, but it's very important to understand how that factor is known to be a driver, but people don't talk about it. And spatially in Alberta, it may be a huge driver. So I want to just close with, by pointing out, now Felix did mention this, but I want to get into it in just a tiny bit, pointing out that this exercise of trend assessment is something all provinces do that have mountain pine beetle, in all states as well. They go out to the field and they measure these R values, which is the number of living eggs, larvae, or adults, divided by the number of entrance holes in a sample. And so when this empirics in BC say that when this value is less than 2.5, populations tend to go down. When it's around 2.5, between 2.5 and 4, they tend to remain about the same. And when they're higher than 4, they tend to increase. A rule of thumb based on experience in BC and nothing more. It's a heuristic method. In SRD, one of the points I want to make is that they don't do quite the same thing. They use a different ranking scheme, and they don't interpret these R values in terms of trend. They just categorize them as low, moderate, high, extreme, because this is based on experience in BC, and we don't have a lot of experience to go on in Alberta. So the fact is this. This method assumes a sex ratio of 2 to 1, females to males. And so one of the reasons that ASRD didn't really want to go the extra step and describe a population trend at these levels was because they were uncertain about all the other things, mortality agents that aren't included in that could be different between Alberta and BC. So they never used this method. They just used this relative ranking scheme. And it appears that it was a smart thing to do because we have this 2 to 1 sex ratio on average in BC, but in Alberta, as Felix just showed, that sex ratio varies from 3 to 1 to 1 to 1, and there's even one plot on the far northern edge where it's even gone male biased from about 1 to 1.5. So it's an important point because that threshold, that critical threshold, is around 2 when populations are explosive. So if you've got 3 to 1, then those populations are explosive and they're almost impossible to control. They grow so fast. 1 to 1, they're far less explosive, reflected in their trend inferences back in BC. So these, from a pest management perspective, these are winnable battles because you've got populations that are going to grow very slowly. So it's very cheap to get into these ones, pull out, cut and burn trees, and have an effective population control. So is population control effective? Well, it sort of depends on what your sex ratios are. And the economics of spread control is dictated largely by this threefold difference in the sex ratio. And it's worth pointing out, too, that these sex ratios, we know from the analyses in the US in the 1970s, that this is a driver of eruptions. We know that endemically they tend to be about even, and then when they get eruptive, they go higher, 3 to 1 to 4 to 1. But no one's ever actually analyzed the population models that they use in BC to see how sex ratio varies over time and space in these models. It's just a big unknown, and it's an opportunity. Clearly, when you've got a threefold difference in population growth rates, you've got a threefold difference in your economics, your cost-benefit ratios of spread control. I'm shocked by seeing all the data that people are producing, Maya and Nadir and Felix and Janice. When we started this in 2006 and made this graphic saying, well, there's 3 different categories of models and different kinds of processes that can be affected, and maybe we'll get some data on 3 of these processes, but every single one of these processes, none of them appears to operate in Alberta and on jack pine in the dry environment the way that they play out in these models, which were all developed based on either US Rocky Mountains data or in BC. They're all different. So our prognostications, we don't really have a firm basis, in my opinion, for doing spread predictions in jack pine. And it's only with the data that these guys, Nadir, Maya, Janice, and the graduate students relating to these processes, all of them, that we're going to be able to make reasonable forecasts. There are 2 ways to summarize how the genomics data gets used. We have a whole bunch of existing models, as I showed, that come from BC. We have a whole bunch of new models that are in creation all the time, and these data get integrated in models, and sometimes these models just directly feed community-based risk assessment processes and at the provincial and at the federal level. And so these genomics data that we gather, sometimes they get integrated in models and get directly used as rate parameters in processes, equations, but sometimes, and leading to enhanced models. So pathway B, genomics enhanced models have an ability to inform decision making at this level, but sometimes we've seen cases, we have a lot of cases now where the genomics data just go bang directly. They pop up on Ottawa's radar screen and they directly inform the policy process. For example, Kathy's paper on announcing that mountain pine beetle was on jack pine. A lot of people said, well, yeah, you know, we sort of knew that would happen, but the actual publication of that observation apparently had some effect, even though people said, yeah, we know, you know, it's no big news. Well, it was huge news, and it had a huge implication. Without that paper, this pathway doesn't get triggered, and the attention doesn't get focused on what's really going on in the system. I don't want to talk a long time for sure, and this isn't my work, the next piece that follows, but everything I've shown you up to now, we sort of conceived of way back in 2006, 2007, when Janice dreamed up this whole thing and asked the question, how can we link population, how can we relate systems genomics to risk assessment if we don't want to be doing biotechnology and producing silver bullets and resistant trees and the weak economics associated with the long time horizons for delivery of biotechnology. Everything I've said so far relates to that question. But another axis to this project, which is in development and going to be delivering soon, is the work being done by Grant Hauer. And his work, I want to just highlight briefly that he's working in two very interesting projects using a very interesting modeling approach. First, we started off working together on the economics of bioenergy options and how the availability of cheap feedstocks resulting from mountain pine beetle kill and provincial policies regarding stumpage on killed timber, how the economics of bioenergy investment changes when you've got beetle in your equation. And in the process of modeling that process, Grant realized that the approach that he was taking was very relevant to the problem of spread control of the Trans-Canada problem of what do you do in terms of controlling mountain pine beetle spread rates across the country. So he's got a model that he's using to do this, what he calls option valuation. And I want to touch on that stuff quickly, but I can't speak to the details of how it's done because it's kind of economic wizardry and outside of my league. But the first aspect is the spread modeling, where he does the valuation of pine across the entire Canadian forest sector. He does some magic to give that a value and a net present value, given that the beetle is expected to move through pine all the way to Newfoundland. So what's the expected spread rate with and without control? So this is a model of that process. Obviously pretty relevant to things in Alberta, but relevant nationally as well. And so in this model, he's got expected values and variability of valuations associated with stochastic prices, control costs, processing costs, etc. And then he's got some details in there and it's a stochastic model. So he's got a lot of uncertainty on expected spread rates and variability driven by weather and other uncertainties. So it's a stochastic model to cope with uncertainties. And then he's got expected damages with and without spread control, and then some economics associated with harvest levels, associated with increased harvesting, salvage, so on and so forth. And he tries to develop what he calls policy functions to determine what you should do under different circumstances, different spread rates and different price points. So it's work that's half done. He's got 2 manuscripts, and the first one, the first stage results show things like this. A variable distribution of expected losses with a probability distribution, the blue with no control, and then with control, and then the red with control. So your savings is the difference between the 2 curves, between the 2 expectations. And so you've got a distribution here because it's a highly uncertain function, both the spread rate and the spread control rate. So what Grant's interested in is 2 things. What are the differences between control and control in the blue and no control in the red, but also what's the value of information. Suppose that you can compress these curves, reduce the uncertainties by doing research, invest a few $100,000 or a few $1 million in research, versus what happens if you spend that money on control. So it allows you to gain how much do you spend on research versus control, which is pretty interesting. So he's actually got some results in this model that shows spread rates, starting with an infestation 200 kilometers just west of Saskatchewan, and with huge variability associated with the uncertainty on what the spread rate is going forward. You'll recall last week I talked about spread rates eastward, and we've observed spread rates of between 80 kilometers and 40 kilometers a year, depending how you want to look at that. But we know that those are going to drop down to some degree as the forest thins out and the population sources start to dwindle. So what Grant has done is modeled the spread rate of between 5 kilometers a year and something like 80 kilometers a year. And so your expectation is out here, but what we're really interested in is the huge variability in this. So for example, the time for the beetle to get to Saskatchewan, which is at the 200 number, may vary between 3 years or it never actually even gets there. So the variability, the uncertainty is so high that you can't predict something like that. And this is a really valuable simulation showing potentially the value of research to reduce the uncertainty on that, so you could start providing people with more robust answers. But this is a very important answer, because we could take this to our federal policymakers and say, well, we can't answer that question, and here's why. So it forces them to cope with the uncertainty around the stochastic nature and the uncertain nature of the spread rates. And in this model, he's also got stochastic pricing. So these prices converge to an equilibrium level, but there's a lot of natural variability in prices, and it's somewhat cyclic as well. And so the point is, this is a stochastic dynamic programming approach. So he has to do millions of runs of this model in order to capture the variability associated with the parameter uncertainty and the stochastic variability associated with uncertain prices. So it's really computationally intensive. And that modeling approach he calls although to date it's a static simulation approach, he's moving toward a stochastic recourse model, which allows you to take these policy functions and make them more flexible and say, instead of asking what do you do in the long run, what's your policy, what's your fixed policy through time, the question is, what is your variable policy tailored to circumstances as the outbreak goes through rapid advances and lots of impact in certain time periods, say during warm weather, or when, say, prices are really low or prices are really high. So he's close to having that model ready and running, which is going to be really, really neat, because then all of a sudden you can do things like evaluate the value of information. So as your research results trickle in, your uncertainty reduces, stochasticity goes down, you need fewer runs. You can say what's the value of what's the direct economic value of reducing that uncertainty in terms of cost savings. So it's pretty cool. But it's also applies to this other problem, and the bigger problem that he's interested in, which is the bioenergy, and where he's asking the question, at what price points, energy prices, at what spread rates, high impact, low impact, do you alter your policy where you take your pine woody feedstocks and divert them away from traditional sources of timber and pulping and divert them into bioenergy. So he's got a model that addresses that, and it's quite the model. I won't get into any of the details on that, except to say, like the other model, it's got all stochastic prices and costs, all kinds of structural assumptions associated with, for example, pellet prices, and how those are driven by policy instruments such as subsidies, price supports in foreign markets. It's quite an interesting model, and even going so far as including things like carbon taxes, prices on carbon. So all this to say that in the same way with the spread control model, the bottom line results for the bioenergy model are that it's really a marginal business proposition. And what you do, the optimal policy, depends very, very sensitively on these price points. And given the large uncertainties on things like spread rates and prices, it's very hard to design an optimal policy. But you can do it, and you can game the situation, given that it's a probabilistic disturbance, given that it's a probabilistic decision whether to control beetle spread, cope with the beetle spread, increase your salvage, or allocate to bioenergies. With this model, you can game those decisions, and you can pick a mixed strategy that allows for multiple possibilities and uncertain possibilities. But that's what Grant wanted me to present, and I guess I'll end there by saying that next year I think he's going to have some pretty, we'll get him here himself to talk about this stuff. But it's pretty cool, and in general, he's advocating this recourse model as a way of government to rethinking the way it approaches policy, going from static policy to flexible circumstance-driven policies. So you have policy functions as opposed to static policies. For example, a static policy would be zero tolerance for mountain pine beetle, or we're going to take all our wood and it's going into solid wood. How do you develop a policy that's a statable policy, that's a coherent, rational policy, but a policy that's flexible to accommodate changing circumstances?